Welcome back, students. In the previous video, we talked about the moving coil galvanometer. The moving coil galvanometer is a simple instrument which has a coil. It's kept inside the two poles, or it's kept between the two poles of a permanent magnet. And if current flows through this coil, then the coil will deflect. And if you attach a pointer to the coil, then the pointer will also deflect along with the coil. And we saw that the deflection angle phi was proportional to the current which is flowing through the coil. The galvanometer is a very sensitive instrument. Even for a very small amount of current, the deflection could be known. Typically, when you design a galvanometer, you design it to handle current in microamperes. For example, I may design a moving coil galvanometer that would handle current of up to say 20 microamperes. So the maximum current my moving coil galvanometer can handle is 20 microamperes. Clearly, you have a coil there, it's a conductor, and it will also have resistance. So the resistance of the galvanometer could be taken to be, say, 50 ohms. I'll call this as the resistance, the RG is 50 ohms. And you have the scale on the galvanometer and a pointer that will point to 0 when no current flows through this. And it will have a full scale deflection. A full scale deflection here for current of 20 microamperes. This is how I've designed this galvanometer. So for no current, no deflection. For 20 microamperes, it will show you full scale deflection. For any value between 0 and 20 microamperes, then the pointer will point at some other angle. And we know that the angle of deflection phi is proportional to the current. So this is what we derived in the previous video. Okay. Now let's see if we can use it in a circuit. Okay. Let's suppose I have a battery 1 volt. This is 1 volt battery, and let's suppose that it's connected to your resistance of, say, 1 mega ohms, or 1 into 10 to the power 6 ohms. I can calculate the current to it. So the current I through the circuit is going to be V by R, and that should give me 1 microampere. So my I now is 1 microampere. So this 1 microampere is within the range of 20 microamperes, that the maximum current the galvanometer can handle. If it is more than that, if it is more than 20 microamperes, the galvanometer will get damaged. So I can pass current from 0 to 20 microamperes in the galvanometer. If there is no current, if it is 0 amperes, then the pointer will be at the 0 position. If it's 20 microamperes, the pointer will show me the full scale deflection. Now I have only 1 microampere flowing through the circuit. So I can connect this galvanometer. Okay, this is a galvanometer. Okay, and this will also have some resistance as the current flows through the galvanometer. So I will call this as Rg. Rg is the current flowing through the galvanometer. Now, I said it's 50 ohms. Yes, Rg is 50 ohms. But would it impact? Because if there is 50 ohms, then there will be a drop here, voltage drop across the galvanometer too. But would it impact it too much, the circuit? No, because you have 1 mega ohms here, and you are connecting only 50 ohms in parallel, in series to that. So the total resistance of the circuit hardly changes. So you will still have almost 1 microampere flowing through the circuit. But one advantage of connecting this galvanometer there now is that it will show you the reading directly. It will show you that, okay, it's 20 ohms, and it will show you a 5% deflection. Then you can read it. So you are using it as an ammeter. What is an ammeter? An ammeter is an instrument that allows you to measure the current flowing through the circuit. So the galvanometer can be used as an ammeter now for currents which are very, very, very small in amount. See, it's 20 microamperes. Suppose I am going to increase the voltage or reduce the resistance. If I do this, if I increase either this or reduce this, the current in the circuit will increase. Let us say that I am going to increase the voltage to increase the current in the circuit. I can do it either way. But I am going to increase the voltage. If I make it 2 volts, then 2 microampere current will flow through this, approximately. If I increase it to 3 volts, then 3 microampere current will be flowing through this. If you increase it to 20 volts, then 20 microampere current will be flowing through this. But if you increase it to 30 volts, then I am in trouble, because the current through the circuit is going to be 30 microamperes, but my galvanometer can handle only 20 microamperes. If I send more current than 20 microamperes through the galvanometer, then the galvanometer can be damaged. The coil could be burnt or something. Okay. So then, how do I? So I have very limited use for the galvanometer to measure the value of current like this. But is there a way where I can improve the range over which the galvanometer can measure current? Right now, it can measure current from 0 to 20 microamperes. Can I make it to measure current from, say, 0 to 10 amperes? Should I go for a new design? Another galvanometer, which can handle 10 amperes. But that's going to be costly. Okay. Particularly for DC, then it's too much. It's not needed. There is no need for you to go for a new design. You can still use the same galvanometer, which can allow only 50 microamperes through it to measure more current in the circuit. So that is what we are going to see now. Let's do this. I have this circuit, V, and let's suppose that I have connected the galvanometer. So this is the internal resistance of the galvanometer. I'll call this as Rg, and there is this resistance R. This could be an appliance, anything. So this is our load resistor. Okay. So this is my I. So this is I in the circuit. But now this I could be say 4 amps or something. Clearly, I cannot connect my RG, the galvanometer here. If I connect the galvanometer here, then I will be in trouble, because it can allow only 20 microamperes, but now this circuit will have say 4 ampere flowing through it, so I will be in trouble. So what should I do? What I should do is that I should somehow, I should allow a maximum of only 20 microamperes to flow through the galvanometer, and the rest I need to bypass. I need to provide an alternative path for the total current. And if the current which flows through the galvanometer is some way related to the total current in the circuit, then I can say I'll be able to decide what is the total current in the circuit if I know the current in the galvanometer. Let's do it this way. Okay. I'm going to provide now an alternative path. RS. So this is the alternative path. I'm keeping a shunt resistance. If you're connecting something in parallel to another thing, then it's called as the shunt connection. So I've shunted the galvanometer here. So this is shunt. So we call this as shunt resistance. So I have a shunt resistance here. So now the current from the battery comes here and breaks here as Ig, current which flows to the galvanometer, and then this would be Is, the current through the shunt resistance. Okay, now, so what do I know? So one thing I know is that I is equal to Ig plus Is. That I know. That is one thing I know. And what's the other thing I know? The other thing I know is the potential difference between this point and this point. I call this as A, I call this as B. Potential difference between these 2 points, okay, can be given by this expression. So B, AB can be given by Ig into Rg, and that is also equal to Is into Rs, because they are parallel to Rs. So that is the second thing I know. Because we connected the 2 resistors in parallel, one is the galvanometer, the other one is the shunt resistance. Since you have connected both of them in parallel, the voltage drop across them must be the same. So I know that Ig Rg is equal to Is Rs. What is Is? Is can be written as I minus Ig. I minus Ig to Rs. So now I've got Ig, Rg. So bring it all, arrange things on the one side. Ig, Rg plus Rs equal to I to Rs. So now Ig is equal to Rs by Rg plus Rs into I. Well, if Rs is a constant, because once you connect to the shunt resistance, you're not going to change it. So Rs is a constant. Rg is a constant again. So this term is a constant. Now note that Ig is proportional to I. So I is the current in the circuit. So I comes here, then I goes through this. It's like that. So if I is the current flowing through the circuit, then the amount of current which is going to flow through the galvanometer is proportional to the current. And the constant of proportionality is this. That's a profound thing, if you think about it. Because using this, I can theoretically use this galvanometer to measure any range of currents. Okay, if I know, all I need to do is that I need to get the appropriate resistance to connect in parallel. Okay, so now let's see. Here, like I said, like 4 amperes is flowing. Let us suppose that I want my galvanometer to give full deflection when the current in the circuit is 10 amperes. Okay. So, then what should be the value of my resistance, RS, the shunt resistance? What I'm saying here is this. My IG max is equal to RS by RG plus RS into this I max. Okay. This IG max I have no control because once the galvanometer is designed, then it can take only a maximum value of current. That's 20 microamperes. That's fixed. I can't do anything about it. That's instrument I have. So this is going to be 20 microamps. 20 into 10 power minus 6 amps. RS I don't know. And RG, I said it's 50 ohms plus RS. Okay. It's the basic stuff. Now look at this, I max. I max I can choose anything. Okay. Suppose I want my galvanometer to measure from 0 to 10 amps. So for 10 amps, when the current through the circuit is 10 amps, my galvanometer is going to show the full scale deflection. That doesn't mean the 10 amps is going through the galvanometer. What it means is that when 10 amps flows through the circuit, then 20 microamps flows through the galvanometer. When maximum current flows through the circuit, then maximum current flows through the galvanometer. Okay, so now this I max, if we take, this is 10 amps. 10. So note here, I should be able to find the RS value using this. So suppose I get some value for RS. Like if we solve this equation, then I will get the value for RS. Okay. So what it means now is that I take the same galvanometer, which can allow only 20 microamps, and if I connect this value of RS, which I figure out from this. I'm not going to do it now, but you can figure out yourself. If you find this value of RS, then if you take that resistance and connect it across the galvanometer, now the galvanometer will show full scale deflection when 10 amperes is flowing through the circuit. Now only 4 amperes is flowing through the circuit. So now the galvanometer will show only 40% of the deflection. So this way, even though the galvanometer can allow only 20 microamperes, you can make it measure more current. I hope this is clear to you. Okay, likewise, if you want to use a galvanometer as a voltmeter, you can do that too. What you would do now for that is, if you have voltage, if this is the voltage you want to measure, the voltage of the battery, then you have a series resistance, okay, and then you connect the galvanometer here. The galvanometer will have the galvanometer resistance. So then what will happen is that this voltmeter will send the current through the galvanometer. Okay, so based on the current that goes through the galvanometer, then the needle will deflect. And again, the full scale deflection will happen when 20 microampere, the galvanometer that we have taken as an example. We said 20 microampere flowing through this galvanometer will give us full scale deflection. So if you want to find full scale deflection, then you need to send 20 microamperes through this. Okay, so this is the galvanometer current, Ig. I call this as Ig. Okay, so the current which flows through the series resistance will also flow through the galvanometer. So this is the maximum allowed current to get full scale deflection. Okay, so this is how you calculate the value of the series resistance we need to connect to this. The series resistance is used to limit the amount of current flowing through it. For example, if this is say 100 volts and if this is 50 ohms again, then if you directly connect it without the series resistance, then what will happen is that it will send 2 ampere current through the galvanometer, which the galvanometer cannot handle. You will damage the instrument. So you are going to have a series resistance. That resistance is Rs. It will be, and this resistance is used to limit the amount of current that flows through this. So if say 100 volts is the maximum voltage that you want to measure, you want to create a voltmeter which is 0 volt to 100 volt range. So if 100 volt is the maximum voltage that you want to measure, then when 100 volt is connected here, then 20 microamperes should flow through this galvanometer. Okay, so what will happen is this. If now current Ig is equal to V divided by Rs plus Rg. So this is the general equation now, right? Okay. This has to be 20 microamps for full scale deflection. So if you want to find, if you want to create a voltmeter which has 0 as the 0 to say 10 volts as a range, then when it is 10 volts, then the galvanometer should show me full scale deflection. So when there is 10 volt connected here, then the current through the galvanometer has to be the maximum current that's allowed. In this case, it's 20 microamperes. The galvanometer that we have taken is 20 microamperes. So if this is 20 microamperes, and if this is say 100 volts, okay, or whatever you want to find, then Rs plus Rg, the resistance of the galvanometer. So Rs plus 50 is a total resistance. So from this you must be able to find the Rs value. Okay. So you take that resistance and connect it across this, then you will be able to get full scale deflection for 100 volts. If it is any other voltage here, say maybe 50, then you will have kind of like half scale deflection. It's 25, 1/4 of a scale stuff. Usually this is a very high resistance, so you will tend to ignore this 50 ohms. This will be in kilo ohms or mega ohms. So when you compare that with just 50, then you can ignore it. So almost a linear scale would be available for you. So this is how you convert a galvanometer into an ammeter or a voltmeter. So to convert a galvanometer into an ammeter, you have to connect the resistance in parallel, and the resistance value will be small. Okay? And if you want to convert a galvanometer into a voltmeter, then you will connect a series resistance to the galvanometer, and the resistance value will be high. Okay? The reason is that for the galvanometer, you need to bypass most of the current. You can only allow microamperes in the galvanometer. The rest of the current should go through another path. So the resistance that you connect has to be small, because only for low resistance more current will flow. But here you have high resistance, because you are trying to limit current through the galvanometer. So when you use galvanometer as an ammeter, a small value of resistance will be connected in parallel, and when you use a galvanometer as a voltmeter, then a very high value of resistance will be connected in series. Hope this is clear to you. With that, students, we have come to the end of this lesson. So I would like to do a brief summary of what we have done in this lesson. Basically, there are only two parts to this lesson. One is the part where we talk about moving charges in an external magnetic field. So what happens to a moving charge when it is kept inside an external magnetic field? It's going to experience a force, and that is given by the Lorentz force equation. Okay? QV cross B, the force experienced by it is given by F is equal to QV cross B. And the second part was about the moving charge creating its own magnetic field, and that was given by Biot-Savart's law and the Ampere's circuitry law. So Biot-Savart's law is equivalent to Coulomb's law in electricity. Likewise, Ampere's circuitry law in magnetism is equivalent to the Gauss's law in electricity. So there are basically these two parts to this lesson, and everything else revolves around these two parts. And once we came across these, Lorentz force, Biot-Savart's law and the Ampere's circuitry law, and we talked about the force between two current carrying conductors. We took two infinitely long conductors, and then we calculated the force experienced by them, either the force of attraction or repulsion experienced by those two current carrying wires. That's obvious, because if one current carrying wire is going to behave like a magnet, the other current carrying wire will also behave like a magnet. So when you have two magnets, then the force of attraction or repulsion will take place between them. So we did that, and then we defined Ampere from that perspective. And once we defined Ampere, we said Coulomb could be redefined in terms of Ampere second. So I mean the charge, the electric charge Coulomb can be defined as 1 ampere second, and that is what you use in SI units. And once this was done, we talked about the electric dipole moment. We said if we take a current and if we make it flow through a loop, then it constitutes a magnetic dipole. So we calculated the magnetic dipole moment of this current carrying loop. We said this M is equal to N into I into A. So where A is the area of the loop and I is the current flowing through the loop, and N would be the number of closely wound turns in the coil if you take. So we talked about that, and once we defined this magnetic moment this way, then we realized that an electron could be treated as an electric dipole. An electron in an atom, when it is revolving around the nucleus, then it is in a loop. So if it is in a loop and if it is moving in one direction, you can consider the current to move in the other opposite direction, but then the current is also moving in a loop. So then clearly this must have an magnetic dipole moment. So we calculated the magnetic dipole moment of a revolving electron in an atom, and we came across what is called as a Bode magneton, and we had its value to 9.217 per minus 34. So that's we ampere meter square. So we came across it too. Very small amount, but then you still have it. An atom behaves like a magnet, okay, in that perspective. So we came across that, and once we did this, then we talked about the moving coil galvanometer, which is to put all that we have learned in practice. Or the theory that we have learned now becomes becomes a practical equipment that you can use. So there, the moving coil galvanometer had only a coil kept between the poles of a permanent magnet, and if you pass current through the coil, then the coil will start oscillating, start moving, will experience a torque because of the arrangement and stuff. And we found that this oscillation could be stopped with the use of a spring. So if you have a spring, then it will deflect and stop. You don't allow it to keep moving back and forth, but then the spring will pull the coil back from moving. So at some point, then the torque on the coil, due to the force experienced by the current flowing through it, and the spring, the torque provided by the spring would match at some point. Okay? And that will give you a measure of the current flowing through the coil. We said phi, the angle of deflection, will be proportional to the current flowing through the coil. And we also talked about how to convert a galvanometer into an ammeter and a voltmeter. A galvanometer straight away can handle only a few microamperes of current. So if you're going to connect it in a circuit, you can, so long as the current is very low in the circuit, you can use the galvanometer as an ammeter itself. But usually our circuits will have much more current than just a few ammeters. So in that case, you cannot directly connect a galvanometer there. So you have to bypass most of the current in the circuit through a shunt resistance. You will have a low resistance. We connect it in parallel to the galvanometer so that most of the current will be bypassed. Only a bit of current will flow through this galvanometer, and there is a relationship you can establish between the current which flows through the galvanometer and the total current in the circuit, which is again linear. So you can recalibrate the same galvanometer to measure different values of current. Even though only microamperes flow through the galvanometer, the amount of current that flows through the galvanometer depends on the amount of current which flows in the circuit. So you can make an ammeter out of a galvanometer like this. And if you take a very high resistance and if you connect it in series with the galvanometer, then you make a voltmeter out of it, because this high resistance is going to limit the amount of current that is going to flow through this galvanometer because of the voltage source. Which range you want to measure the voltage depends on what value you are going to have for the resistance, external resistance. Likewise, which range you want to have your galvanometer to measure the current depends on the value of the shunt resistance you have, the parallel resistance you connect with the galvanometer. So these are the two things that we talked about when we came across galvanometer. And that's about it as far as this lesson is concerned. This is a very quick summary of this lesson, and the rest are all details. If you understand the lesson well, then there is nothing in the lesson basically. It's a very easy lesson if you understand it. So go through the videos, and if you have any questions, doubts, clarifications, if you require any clarifications, you reach out to me and I will respond to you. So I consider this lesson to be complete. In the next video, we'll take the next lesson.